method. Okay, and then
hello,
Dr. Arwa. Dr. Arwa. Maybe it's not available at the moment. So,
yeah, I think so.
Dr. Alwar. So, I'm sorry for the
Oh, it's okay.
technical
It's
problem.
okay.
So,
Yeah.
now we are going to have a photo session to all participants. Please turn on the camera and use the virtual background that we have attached in the chat room. Once again, to all participants, please turn on the camera and use the virtual background that we have attached in the chat room. And to Mr. Hakim, oh yeah, to Mr. Hakim, please help us to capture the image of the webinars.
okay, thank you, Mr. Gani. Okay, please turn on your camera. For the first slide, 1, 2, 3. Okay, next. 1, 2, 3. Okay, thank you, Mr. Gani.
Okay, thank you, Mr. Hakim. Now we will go to the main agenda of the topic of about structure calculation of diatomic molecules using a initial method with our speaker, Dr. Renu Bala from Center for Quantum Engineering, Kolkata, India. This talk will be moderated by Dr. Salma Haminati. To Dr. Salma Haminati, the screen is yours. Please.
Okay, thank you. Okay, now I'm a moderator uh, in this talk. Okay, first I want to introduce myself. My name is Salma Haminati. I'm a lecturer in chemistry department of Islamic University of Indonesia, and we are. I would like to introduce our speaker today. Yeah, let me share. Okay, okay, okay. Okay. She is Dr. Renu Bala. Yes. Now, she is doing a postdoctoral fellowship in quantum engineering of research and education TGC Crash Kolkata, India, and her research interest is about ab initio calculation for electronic structure and properties of atom and molecule, symmetry violating properties of atom and molecules, atomic and molecular clocks, application of quantum computing in the field of quantum chemistry, and her research experience is about the calculation of electronic structure and properties of atom and molecules. And I was I met her when in Japan, so we are in the same we are in the same supervisor. The our supervisor is Dr. Minori Abe. Yes, we are doing in the same laboratory. Okay, then she know more of about the codes for atomic molecular structure about C4, Dirac, MRCC, MOLCAS, and this level of the Fortan program. So you see, her education is was graduate from Indian Institute of Technology roles in the field of theoretical atom and molecular physics in Indian Institute. This he get her PhD, and her supervisor is Dr. Nataraj from Punjabi University in the and the yes, and then she graduate from Master of Science in Physics in Punjabi University, and then her bachelor is from College of Science Education and Research, Jaragon, Punjab University, India. Okay. Yes, her teaching experience, yes, she was the tutor for bachelor student this year, bachelor student in physics course, and her award is she get GST Trust Fund for visiting Tokyo Metropolitan University from June until July in December in 2017. This I met her and we are going in the same conference. And then this she gets senior research fellowship from India, and she get university grant commission, and etc. And she more family. She use Linux and programming language of Fortran, and this is her publication. Yes, her publication is okay, and this is many calculation about ab initio calculation. Yes, this is of the Minora AB is my supervisor also. Yeah. This is the conference paper. And many oral presentation and participation in conference was joined. Okay. Next, okay, I will give this time to Miss Venubaya. Okay, time and yours. Thank you.
Thank you, Dr. Salma and other organizers for organizing this lecture. Shall I start?
Yes.
Okay, thank you. I'm going to share my screen. Are you seeing the screen? Hello, are you able to see my screen?
Yes, very clear.
Yes.
Okay,
Yes.
okay, thank you, thank you. Thank you. Good morning to all of you. Again, I would like to thank all the organizers for organizing this lecture. The title of my talk is Structural Study of Atomic Molecules Using Ab initio Methods. The overview of my talk is, first I'll give the introduction and the motivation that why diatomic molecules are important and what is the motivation that why we are doing the structure calculations. Then I'll discuss some of the basics of the diatomic molecules, means the basic structure that will in which I'll talk about the basic structure parameters, which will be followed by the many-body methods and the basis sets that can be used to evaluate the various structure parameters. And at last, I'll show some results for the diatomic molecules. Since the study of cold and ultra cold molecule is one of the fastest growing field in the modern molecular physics. So although the molecules has complex structure than atoms, but with the careful... Hello.
Can you this F5 to make the screen bigger?
Okay, fine, yeah.
Okay.
Let me try. Okay, fine, yeah. So the study of cold and ultra cold molecules is one of the fastest growing field in the modern molecular physics. Although the molecules has complex structure than atoms because of the presence of vibrational and the rotational levels, but with a careful study, we can obtain the wealth of information that can be used to explore the various areas of physics, chemistry, and also the interrelated areas of research. For example, if we see the equation 1, we can see the electronic transition is directly proportional to the mass of the electron. And according to the equation 2, the vibrational frequency depends upon the mass of the electron as well as the mass of the proton. So if we take the ratio of 1 and 2, that means we can measure the variation by measuring the variation in the ratio of the frequency of vibrational and the electronic transition. One can measure the ratio of the electron to the proton mass ratio, as this ratio is directly proportional to the square root of the electron-proton mass ratio. Similarly, if we take the ratio of the rotational frequency with the electronic frequency, it is directly varies with the ratio of electron to the proton mass ratio. That means if we measure the variation in this ratio, that means the variation in the frequency ratio, one can measure the frequency in the mass ratio. The diatomic molecules can also be used to study the variation in fine structure constants. These can be used to study the electric dipole moment of an electron. Although classically, if we think that there is no dipole moment for a single particle, but in the quantum field theory, each particle is surrounded by the particles and antiparticles. Therefore, whenever there is a disruption from the spherical symmetry, then there is electric dipole moment of an electron. And the molecules can be used to measure this electric dipole moment of an electron that can be further used to explore the physics beyond the standard model. Our current standard is cesium standard. And after that, in the cesium, there is one hyperfine transition that works as a frequency standard. After that, there are several atoms and ions have been proposed whose frequency lies in the optical region. But nowadays, researchers are looking for the molecules that in molecules, particularly the vibrational transitions that can be used for the frequency standard, and their frequency lies in the optical region. The other fields such as quantum computing, quantum phase transitions, two species bose-Einstein and condensations, the collisions of the molecules and atoms at low temperature, chemical reactions in a controlled manner, and ultra-cold plasmas also use the diatomic molecules at cold and ultra-cold level. There are several techniques have been developed for the formation of such molecules. For example, cold molecules. Cold means whose temperature lies in between the 10 millikelvin to Kelvin range, can be formed using the buffer gas cooling and electrostatic trapping. The ultra-cold molecules means whose temperature less than the millikelvin can be formed via photoassociation and the Feshbach resonances. The molecular ions can be formed using the sympathetic cooling using laser-cooled atomic ions. And for the design and development of such experiments, various theoretical inputs from the diatomic molecules such as potential energy curves, from which one can extract the spectroscopic constants such as equilibrium bond length, dissociation energy. Omega E is a harmonic frequency, omega E X is an harmonic constant, BE and alpha is a rotational constants, and TE stands for the transitional energies. The molecular properties such as permanent dipole moment, theta stands for the quadruple moment, then alpha parallel and perpendicular represents the components of molecular polarizability. A parallel and A perpendicular represents the components of hyperfine structure constants. And the last is an effective electric field. The molecular formation rates and the vibrational parameters such as vibrational energy, vibrational rotational constants, vibrational dipole moments, lifetimes of the vibrational levels, and transition dipole moments. Such kind of theoretical input parameters are required for several experiments to understand the fundamental point and as well as for the design and development of the various experiments. To perform the calculations of the spectroscopic parameters, we need to think about about the basis set and the method used for the calculation. Means the accuracy of these parameters theoretically depends upon these two factors. I will talk about the basis sets and the methods, but before that, I would like to discuss some basics of the diatomic molecules. The simplest approximation for the diatomic molecule is the harmonic approximation, in which it is assumed that each particle, the two atoms are joined by a spring of spring constant K, and this follows the simple harmonic motion. That means this curve is parabolic in nature, and all the vibrational energy levels in this parabola are equally spaced. And the potential, this harmonic potential, can be given by the first equation. In this equation, K is the force constant, R is the internuclear distance between the two atoms, and Ra is the equilibrium bond length. And this force constant can be calculated as a second derivative of potential with respect to the internuclear distance. And the frequency of oscillation is given by expression 2, where again K is a force constant and mu is the reduced mass of the system, which can be calculated as product of M1, M2 divided by M1 plus M2, where M1 and M2 are the masses of the atoms that forms a diatomic molecule. And then the energy of this vibrational level is given by equation 3, where V is the vibrational quantum number, H is the Planck's constant, and omega is the frequency of oscillation. This vibrational quantum number can take the values 0, 1, 2, 3, and so on. For V is equals to 0, our energy eigenvalue is not equal to 0. That means even the atoms in a molecule never at rest with respect to each other. Further, if we continuously stretch the molecule at a particular distance, the molecule will dissociate into the atoms, and that limit is known as a dissociation limit. So at that point, the potential is no longer a harmonic potential. That means an harmonicity comes into picture. So then an harmonic potential represented by the blue curve is represented by the equation 4, that is known as Moore's function, where in this expression, where D is the dissociation energy and A is the constant of a molecule that has a dimension reciprocal of distance, means reciprocal of R. So in the presence of that anharmonic effects, the energy eigenvalues for the vibration state is given by expression 5, where Xe and Ye represents the anharmonicity constants. And as we move towards a higher order term, the contribution goes on decreases. So the major contribution comes from the quadratic term. And in this approximation, the maximum number of vibrational states can be calculated using expression 6. Because of this anharmonic terms, the difference between the vibrational levels goes on decreases. As we can see the red lines, the relative separation between the vibration level decreases as we move towards a dissociation limit. That happens due to the presence of anharmonic effects. That means as we move towards a higher states, that anharmonicity effects will increase. Further, for a single rotation, there are several vibration occurs in a molecule. Therefore, the total energy of the system should be the sum of vibrational energy and the rotational energies. So in the expression 7, the first term corresponding to the vibrational energy and the second term corresponding to the rotational energy. where V represents the vibrational quantum number and J represents the rotational quantum number. In this expression, this VE represents the rotational constant that is inversely proportional to the I, which is known as moment of inertia. And moment of inertia is directly proportional to R square, as the reduced mass for a particular molecule will be constant. Therefore, B is inversely proportional to R square. Due to the inverse dependence, the rotational constant will decrease with the increase in the average R between the two atoms. And D is a centrifugal distortion constant. So that means each vibrational level in a one electronic state has a different rotational constant. And that can be calculated using this expression 8, where PV is the vibrational rotational constant for particular vibrational level V, and BE is the rotational constant corresponding to the actual equilibrium point. And alpha is a positive constant, which is for a particular molecule is different. And V is the vibrational quantum number. So to perform these parameters that I have discussed, like rotational constant, vibrational parameters, energies, we need the many-body methods. The simplest, the necessary thing that we have to perform is the Schrodinger wave equation. Means we have to solve the Schrodinger wave equation to calculate all these parameters. If we have an electron system with m nuclei, the total Hamiltonian for that system is given by second equation, in which the first and the second term represent the kinetic energy term of electron and kinetic energy term of the nucleus. Then the next term represents the interaction between the electron and the nucleus. Then 1 by Rj terms represents the interaction between instant Coulomb repulsion between the two electrons. And then the last term represents the interaction between the two nuclei. This whole expression is written in terms of the atomic units, in which H cross and E means the charge on an electron is considered as 1. So the total wave function of this system can be written as the sum of, as a function of electronic and the nuclear coordinates, where R represents the electronic coordinates and A represents the nuclear coordinates, and which can be further written as a product of two functions, that is electronic wave function and the nuclear wave function. Since, as we know, the mass of the nuclei is much larger than the mass of the electrons, therefore the kinetic energy of the nuclei, that means the second term in expression 2, can be ignored. And with this approximation, the last term will become constant because of R constant and there is no motion. So this term becomes constant. And the rest of the three terms will give us the electronic Hamiltonian. So, and this approximation where we ignore the motion of the nucleus and we separate the nuclear and the electronic motion is known as a Born-Oppenheimer approximation. Then by calculating the energy using this electronic Hamiltonian, we'll combine that electronic energy with this constant term that will form a potential for the nuclear motion. And then by solving the nuclear Schrodinger equation, we'll get the total energy of the system. Coming back to this expression 4, we can see that the last term present is a 2 electron term. Therefore, it is not possible to solve the Schrodinger equation exactly because of the presence of this 2-body term. Therefore, the Hartree gave an approximation in which he assumed that each particle is moved in an average potential created by all other particles, and that potential is known as the average potential. And the difference between the exact Coulomb repulsion and the average potential is known as a residual potential. In this approximation, the electronic Hamiltonian can be written as a sum of H0, where the potential is replaced by the average potential and the residual potential. And therefore, the difference between the correlation, the difference between the exact energy of the system and the Hartree-Fock energy. Hartree-Fock energy means the energy that has been calculated using the Hamiltonian H0. And that difference is known as the correlation energy. And to calculate this correlation energy, we need the post-SCF methods. So in post-SCF methods, The exact wave function is generated by taking the all possible excitation with respect to the reference state. I mean the reference state is either the Hartree-Fock state or the Dirac-Fock state. If we are performing non-relativistic calculation, then our reference state will be the Hartree-Fock state. And if we are performing relativistic calculation, then our reference state will be the Dirac-Fock state. So then we have to consider all the single possible excitation, and sum of all the term represent the single excitation process. And similarly, we have to consider the double excitation process, and sum of all this term will give us the exact wave function. I'll talk about the different methods in my upcoming slides. And there are three main methods that has been used to perform the electron correlation calculations. One is a configuration interaction method. Next is a many-body perturbation theory. And last is the coupled cluster method. I will talk about in brief about these methods in my next slides. First is the configuration interaction method, in which the exact wave function is given by equation 1, where phi naught is the reference state, that means the Hartree-Fock state. And the next term represents the all possible single excitations. For example, if we see this diagram in which all red color lines represents the occupied spin orbitals and all the blue color lines represent the virtual ones. And if we consider the one excitation at a time, that means the particle is the electron, and here I represented this electron by star. And if we consider the excitation from the filled orbital or the occupied or spin orbital A to the unoccupied orbital R, then we get the excited determinant phi AR, and the corresponding coefficient is represented by CAR. That means here we consider sum of all these terms possible with respect to the single excitations. Similarly, the next term represents the double excitation, in which the two particles simultaneously excite from the filled orbital to the virtual ones. So, by considering all possible excitation, if we consider this term, this is known as the full configuration interaction method. And this constant term represents the amplitude corresponding to these excitations. In the symbolical form, this can be written as equation 2. If we consider all the n-tuple excitation, then this method is known as full configuration interaction method, and the energy that we'll get is the exact energy. But due to the practical limitation, it is not possible to get the exact energy to solve. So we have to truncate this expression at somewhere. Usually the truncation is used up to the double excitation. And in that truncation, this method is known as configuration interaction singles doubles. But in the truncated form, it has some limitation. And the main limitation is the truncated CI is not size consistent. Now, what I mean is by size consistent, for example, we have two systems, system A and system B. Then the energy of the individual system must be equal to the energy of the total system. But in this method, this is not so. Or we can say the energy of the system doesn't increase linearly with the increase in the number of particles. So the truncated CI is not size consistent. And this represents the full CI matrix, in which we can see that the matrix element between the reference state and the single excited determinant is 0. That is the result of the Brillon's theorem, according to which the reference state cannot be mixed with the singly excited determinant. And also we can see all those matrix elements in which the reference state and the excited state determinants are differ by more than 2 orbitals. For example, this phi naught and sorry.
Okay. This is no problem. Okay. Hello, participant. Do you have questions? Please, just ask to me. I will tell to Miss Renu. Hello.
Hello.
Okay.
Hi. Means first I have to take some questions, or I have to continue and take the questions at the last.
I think continue is okay. Yes.
Okay. Shall I go ahead?
Yes.
Okay, thank you. So what I'm talking about is, if we see the first row and the fourth column, this element is 0 because the reference state phi naught and the excited state determinants are differ by 3 orbitals, means the 3 excitations A, B, C take simultaneous excitation to the virtual ones RST. That means all those orbitals or all those matrix elements in which the reference state and the excited terminants are differ by more than 2 orbitals will be 0, because the maximum in our Hamiltonian, the maximum term is the two-body operator. The next method is the many-body perturbation theory, in which the exact wave function is given by expression 1, where phi naught is again the reference state that can be Hartree-Fock or the Dirac-Fock state. And the next there, L represents the order of perturbation and J represents the order of excitation, where K, J, L correspond to the coefficient of the wave function that represents the Lth order of perturbation with the Jth order of excitation. The main advantage of this method is it takes the all n-tuple excitation at each order of perturbation, due to which it is size consistent in nature. But the disadvantage of this method is the number of terms increases very rapidly at each order of perturbation. Therefore, it is very difficult to extend this method beyond the 5th order. And also this method is non-variational, so there is no upper bound to the energy. And the next and the most useful method is the coupled cluster method, in which exact wave function is generated by operating the exponential operator on the reference state. In the exponential operator, T is the excitation operator that can be written as a sum of single excitation operator, double excitation operator, and so on. Because of this exponential nature, it includes a linear as well as a nonlinear term. For example, even if we consider T1 and T2 in this expression, we can generate the triple excitation with the combination of T1 and T2. Similarly, the quadruple excitation can also be generated by taking the T2 square or T1 raised to power 4. So it includes a linear as well as a nonlinear terms. Because of the presence of linear and the nonlinear term, this method is fully size consistent at each order of perturbation. And also because of this nonlinear terms, it takes into account the large number of correlation effects than any other method at the similar level of truncation. In second quantization form, these T1 and T2 expression can be written in this way, where T, A, P represent the excitation amplitude, in which the particle from the filled orbital A will go to the virtual spin orbital space P, and AP dagger and AA represent the creation and annihilation of the particle in P orbital, and particle is annihilated from the A orbital. In the diagrammatical representation, it can be represented as where blue horizontal line represents the Hartree-Fock state, and the arrow towards the vertex represented by A orbital represents the annihilation of the particle, and the arrow away from the vertex represents the creation of the particle. Similarly, this is for the double excitation, in which the two particles from P and Q orbitals are get annihilated, and the particles in orbital A and B get created. So these methods, these theoretical methods should be combined with the basis set to calculate the structural parameters. Now, what are the basis sets? First, a basis set is a set of known functions, chi I, which can be used to construct the wave function phi, where chi I is a number of means the known functions, and C are the coefficients. So exact wave function is considered as a linear combination of all known functions. Ideally, the basis set can be of any form. It can be exponential type, it can be of polynomial, it can be of Gaussian type. But for the electronic structure and structure calculations, usually people use either the STOs or the GTOs, means Slater type orbitals or the Gaussian type orbitals. So the Gaussian type orbitals has some slope, has zero slope at r is equals to 0 because of the presence of this r square term. That's why it required the more number of orbitals than the Slater type orbitals. But The advantage of the Gaussian type orbital is the electronic integral calculations are easier and faster with GTOs rather than STOs. Therefore, GTOs are most commonly used for the theoretical structure calculations. And in this expression, N represents the normalization constant, YLM represents the spherical harmonics, R is the radial distance, N represents the principal quantum number, and zeta and chi represents the Slater and the Gaussian exponents. So using this basis sets theoretical methods, we can calculate the various parameters. This is the overall graph algorithm. Means first we have to choose some ab initio method. We need to combine that with the basis set, and using that we can calculate the spectroscopic constants such as equilibrium bond length, dissociation energies, and the various energies of electronic level, vibrational, and the rotational levels. We can also perform the molecular properties such as dipole moment, quadrupole moment, polar components of polarizability, lifetimes, and also the hyperfine structure means the core properties such as hyperfine constants, effective electric field, etc. Further, different parameters can be used to calculate. For example, these energies can be used to calculate the variation in the electron to the proton mass ratio, fine structure constant. These molecular properties can be used to find the various shift in the frequency standard, such as Stark shift that occurs due to the electric field, Zeeman shift due to the magnetic field, and BBR shift, etc. And also, depending upon the value of the dipole moment, one can study the dipole-dipole interactions, long-range dipole-dipole interactions actually. And then the hyperfine structure constant, effective electric field, etc. can be used to explore the physics beyond the standard model, means to calculate the electric dipole moment of an electron. That can be further used to understand the physics beyond the standard model and the grand unification theories. And then further, all these properties and shifts can be used in the design and development of the various experiments related to cold and ultra cold molecules. Here I am going to show some results for some molecules for all the spectroscopic parameters. Here I choose two molecules, MgLA plus and CLA plus. The motivation behind this work is the elastic collision between the laser cooled fermionic lithium atoms and the calcium ions have been studied by Hayes et al. To observe the atom-ion interaction. This MgLA system has been recently considered for the study of elastic, inelastic, and the photoassociation processes. For these two molecules, till now, there is no experimental data available. And also the theoretical calculations available are very few. And all the calculations that has been available in the literature has been performed using the effective core potential. Now, what I mean is by the effective core potential is, for example, for MgLI, we have 14 electrons, in which the 12 electrons is considered as a core, and all the calculations will be performed with respect to the last valence electrons. That means all the even if we're considering the double excitation, means because there is only 2 electrons. With considering the double excitation means we're actually doing the full configuration interaction method, because all other 12 electrons are considered as a core. So there is some constant energy is taken from that core. So, but in our calculation, we have performed all the calculations using by considering all the field and the virtual orbitals as active. And for these calculations we have performed, we have used C4 and the Dirac softwares that are open source softwares. Only you need to apply for the license. For the basis set, we have used a triple zeta and the quadruple zeta basis set. Now, what I mean by triple zeta and a quadruple zeta? For example, if we have a neon, so in that case, 1s2, 2s2, and 2p6. So that is a minimal basis set. If we're considering each orbital, one orbital corresponding to each filled atomic orbital. But if we add one extra function to each orbital and one orbital at the highest angular momentum, so then it is known as a double zeta. Similarly, we add 2 extra functions to the minimal basis set, then it is known as triple zeta. And similarly, if we add 3, it will be q zeta and so on. As we know, we are dealing with a diatomic molecule that is a heteronuclear diatomic molecule. And in the heteronuclear diatomic molecule, the highest symmetry possible is C infinity V. But with all the softwares, we have to strict with the C2V that has 4 elements. One is the identity, and then second is the C2, that means a 2-fold rotation. If we consider a molecule lying along the z-axis, then we have 2 reflection plane. One is xz, another is yz. So all these calculations have been performed using the C2V point group symmetry. So this graph shows that the potential energy curve for the MgLA plus and CLA plus system at the relativistic and the non-relativistic level, where blue curve represents the non-relativistic calculation corresponding to the non-relativistic calculation, and the red one represents corresponding to the relativistic calculation. So as expected, the relativistic energies are lower than the non-relativistic one. In order to understand the dissociative nature, because it's the ionic system, so there are 2 possibilities. For example, MgLA plus can be dissociate as Mg plus and Li. And the other possibilities, it can dissociate as atomic magnesium and ionic lithium. So to understand this, we have compared the ionization energy of the neutral molecule with the ionization energy of the lithium. And we have both atom Mgi and Li. And we have seen that ionization energy of the MgLi or CLi matches with the ionization energy of the lithium. That means we can say that our molecular ground state will dissociate as atomic magnesium and ionic lithium. The next graph shows that the behavior of the permanent dipole moment curve as a function of internuclear distance. And since the expression is permanent dipole moment has E is equal to E into R, so it varies linearly with the increase in internuclear distance. It increases because of the presence of ions. If the systems are not ionic in system, then the dipole moment will goes to 0 after a particular distance as we are moving towards the dissociation limit. So this table shows that the results for the spectroscopic constants that has been extracted from this potential energy curve. Our results are shown in the bold font, and other one are the results available in the literature. Here you can see we have also quoted the error bars. So all the calculations that we are performed or everybody is performing in this field are approximation in one way or the other. So in our calculation, we have considered the source of error from the 2 sources, because we are mainly depend upon the basis set and the method. So if we consider there is 2 sources of error bar, delta 1 and delta 2, where delta 1 is the error bar that comes from the basis set, because as we increase the number of functions in our basis set, we are calculating the accurate results. We are moving towards a complete basis set limit, but practically it is not possible to consider it performing the calculation using the infinite basis set. So we have taken a difference between the results at CCSD with partial triple level at T zeta level and Q zeta level. The difference between them is considered as delta 1, and delta 2 is considered due to the method used. So for example, if we consider the excitation CCSD, double excitation, then the triple excitation and the quadruple excitation, the contribution goes on decreases. The highest contribution will come from the double excitation. So the difference between the coupled cluster single doubles and the coupled cluster single doubles with partial triple has been taken as the error bar, which is considered as delta 2. Except for one reference, all other calculations that have been available in the literature has been done using considering the system as a 2-electron system, and the active space considered is very small as compared to ours. Okay, this table shows results for the molecular properties for the ground state of MgLA plus and CLA plus system. Except for dipole moment, all other properties we have reported for the first time, where mu z stands for the dipole moment, theta stands for the quadrupole moment. Since we are dealing with the diatomic molecules and a molecule lying along the z-axis, and therefore the z component of the dipole moment is equal to the negative sum of the x and y components of quadrupole moment, where this alpha parallel represents the z component of polarizability and alpha perpendicular represents the x and y components of polarizability. And this x and y components are equal because molecules are linear and a molecule lying along the z-axis. And by using the parallel and perpendicular components of the polarizability, we have calculated the average and anisotropic components of polarizability using average alpha bar can be calculated as alpha parallel plus 2 times alpha perpendicular over 3, and gamma can be calculated as the difference between the parallel and perpendicular components. And to check the accuracy of our result, we have performed the polarizability calculation at the dissociation limit, that is 100 atomic unit distance, where the molecule will dissociate into the atoms. And then the sum of these, the polarizability of the molecular polarizability is equal to the sum of the atomic polarizabilities, and our result match well within the error bars. The next, this is the graph. This graph shows the behavior of the quadrupole moment as a internuclear distance, and as expected, it varies as r square with respect to r. And then this graph shows that the behavior of the dipole polarizability, where red curve represents the parallel component and the blue curve represents the perpendicular component. And after a particular distance, say 15 angstrom, both the parallel and the perpendicular component will same because the molecule will dissociate. And in the dissociated, there is no interaction, so that polarizability is both parallel and the perpendicular components are equal and equal to the sum of the atomic polarizabilities. Next, this graph shows that the potential energy curves for the excited states of MgLA plus system. To understand the dissociative nature of this, we have compared our energy in the molecular system with the sum of the atomic energies. And we have seen this, this is singlet sigma. This is again singlet sigma. This 1, 3 sigma means a triplet sigma and then triplet pi. And our result, except for triplet pi, all other result, the energy difference between the our calculated in our work and that taken from the NIST means the sum of the atomic energies, the difference is less than 1%. And then this table shows that the results for the spectroscopy constant, which are extracted from the potential energy curves for the excited state of MgLA plus system. There is only 2 publication available for the excited state of MgLA plus system. And these calculations have been performed using the effective core potential. So this graph shows that the behavior of the permanent dipole moment as a function of internuclear distance for the excited states of MgLA plus. In this graph, we can see there are 2 groups. There are for some states at large distance, some states has positive dipole moment and other has a negative dipole moment. And it can be understood from the dissociative nature. All those states which are dissociating into ionic magnesium and atomic lithium has positive dipole moment. And on the other hand, all those states which are dissociating into atomic magnesium and ionic lithium has negative dipole moment. That means the sign of the dipole moment will change with a change in the polarity of the system. And it can be the other way around because while performing this calculation, I have considered my magnesium atom at the origin and vary the distance for lithium atom. But if we change if we keep the lithium atom at origin and weigh the distance of magnesium, then the positive dipole moment will become negative, and the negative, all those states which has negative dipole moment at the large distance will become positive. And then this, the next graph shows that the behavior of the transition dipole moment with respect to the ground state, that means the singlet sigma state. All those transition from singlet to triplet are not allowed transitions because according to the selection rule, delta S should be equal to 0. So there is no transition from singlet to triplet. There is only singlet to singlet transition. And also you can see that the transition dipole moment will goes to 0 after as we move toward the dissociation limit. This is because these transitions are not allowed atomic transitions. Similar to MgLA plus, these are the potential energy curves for CLA plus system. And these are the dissociating states, and then the energy comparison of both performed in our work and that taken from the NIST. These are the expected spectroscopic constants for the low-lying excited states of calcium-lithium system. Except for equilibrium distance, dissociation energy, and harmonic frequency, all other properties we have reported for the first time to the literature. Similar to MgLA plus system, we have seen that for CLA plus system also, with the change in the dissociative nature, the polarity of the sign of the dipole moment will change. And also for the transition dipole moment, the transition dipole moment goes to 0 because of the forbidden atomic transition at the large distance. Then by using the potential energy curves and permanent dipole moment curves for the electronic state, we have solved the vibrational Schrodinger equation to calculate the vibration parameters such as vibration state energies, rotational constants, and the transition dipole moments. Further, by using the relative energy separation between the vibrational level and the transition dipole moment between the vibrational level, we have calculated the spontaneous and the Bezier-induced transition rates, which are given by this expression where gamma emission represents the emission transition rate and gamma absorption represents the absorption transition rate, where n bar represents the average number of photons. In this expression, h bar is the Planck's constant. Omega delta V represents the relative energy separation between the vibrational levels. Kb is the Boltzmann constant, and T is the temperature, that is 300 Kelvin. And the gamma absorption and the emission transition rate varies as the cube of relative energy separation and the square of the transition dipole moment between the vibrational levels. And this graph shows that the relative energy separation between the vibrational levels, for example, the yellow curve represents the relative energy separation between the vibrational levels for the ground electronic state. And we can see the relative energy separation goes on decreases because of the presence of anharmonic effects. And the anharmonic effects are large near the dissociation limit. That's why the relative energy separation is very small between the vibrational levels near the dissociative limit. So similar for this red represents the number of has maximum number of vibration level 20 and so on. And similarly, this curve shows that the relative energy separation between the vibrational levels for ground as well as for the excited state of CLA plus system. This now shows the behavior of the lifetime as a function of vibrational quantum number. The lifetime for this blue curve represents the lifetime of the MgLA plus system, and the red curve represents the vibrational lifetime of the vibrational state for CLA plus system. In this case, we can see the lifetime decreases up to a certain point, and then for the highest vibrational state it again starts increasing. And for MgLA plus system, it is found that for V is equal to 0, that means the lowest vibrational state of ground state, and the lifetime is 2.81 seconds. And for the highest vibrational state, it is 19.3 seconds, which is much larger than that of the ground state. Similarly, for CLA plus system, the ground vibrational state The lifetime of the ground vibrational state is found to be 3.19 seconds. And for the highest vibrational state, it is comparable to the ground state and it is equal to 2.38 seconds. This nature of the curve, that means first it decreases and then increases, can be understood from the transition rate. This red curve represents the black body radiation induced transition rate, and blue one represents the spontaneous transition rate. And both first increases and then decreases. The lifetime is a reciprocal of the transition rate, and hence it follows the opposite trend. So this is the summary of this work. Means we have performed the potential energy curve, permanent dipole moment curve, and then extracted the spectroscopic parameters and the molecular properties for the ground and low lying excited states of these systems. Then we have performed the calculated spectroscopic constants and the dipole moments have been compared with the existing data in literature. For the quadruple movement and the dipole polarizability, there is no calculation available in the literature. We have also quoted the error bars due to the basis set and the correlation effect. As the calculated permanent dipole moment at RE for both MgLA plus system and CLA plus system is sufficiently large, so these molecules can be used to study the long-range dipole-dipole interactions. Further, by using the potential energy curves and permanent dipole moment curves, we have calculated the vibrational parameters, and it has been found that the lifetime of the highly excited vibrational state for the electronic ground state is much larger than the ground vibrational state for MgLA plus system, and it is comparable to the ground vibrational state for CLA plus system. And such high lifetimes are required for several ultra cold experiments. And with this, I would like to thank all of you for listening my talk. Thank you.
Okay, thank you very much, Renu, for very
Thank you so much.
very interesting lecture. Yes. Okay, then we continue in the question section. So
Okay.
For the participant, if you have question, please ask. You can put the message in the chat room or just ask to the speaker. Thank you. Okay. Maybe first from me.
Okay. Yeah. Sure.
Yeah. So you explain about the theory and you use like Dirac program. Yes.
I have used C4 as well as Dirac.
And Dirac.
Yes.
Yes.
Yeah.
Because for me, I don't have experience with Dirac and C4, and is it I mean, if we run with this program, can we get what is the energy of this? For example, we want to get the Gibbs free energy, and is it possible?
Which are you talking about? Which energies? The total electronic energies.
Total electronic energy.
Yes. Total electronic energies as well as the individual orbital energies are possible both in Dirac as well in C4. Means we can see that up to which orbital we want to restrict. Means what is our cutoff. So we can see the individual orbital energies, and using that we can even perform the truncated calculations.
So it is possible to get the Gibbs free energy, the total energy.
You means to say Gibbs free energy?
Yes.
No. I don't know. I don't think so. The Gibbs energy is possible because can you explain what is the Gibbs energy? Gibbs energy is somewhat different from the electronic energies. It is related to some ionization of molecule or something.
Yes, yes. Because if I use Gaussian program, then
Mhm.
in the output, this is earliest like Gibbs free energy, entropy.
No, entropy is not possible with the Dirac and not even with C4, as far as I know. But to calculate the ionization energy, what we can run two different calculations. One is for the ionic system and other is for the neutral system. And then we can take the energy difference between the two to calculate the ionization energy. But entropy is not possible. Means to my experience, I'm not interested. I have not explored in that way. But as far as my understanding and my knowledge, it's not possible.
Oh, okay. Yes.
Yeah, thank you.
Okay, thank you. And then about the basis set. The basis set you explain about the Slater use Slater
Determined.
and Gaussian basis.
Yes. Yeah, yeah.
Which one is better? Actually, if I have for example, like you tell us about uh, magnesium or lithium, this which is better actually for
Actually, in general, if we see that there are more advantages than for STOs. Because if we want to use GTOs, we need to consider more number of orbitals than for the case of STOs for the same accuracy. But the point is the calculations with the GTOs is easy because of the R square presence. So for plus R and minus R, there is no need to repeat the calculation. So the integral calculations are easy with the GTOs rather than STOs. So in the literature, generally people are using Gaussian type orbitals rather than Slater type orbitals. Yeah.
Okay. Thank you. Okay.
Thank you.
Okay, next. Our participant, please ask question. Okay, then sorry, maybe I saw this okay, if the you explain about the error of the pi system is larger in this slide, I think.
So, sorry, what is larger? I don't understand.
The error.
Error. Okay,
Yes.
error. Okay, okay. Let me go to that slide.
Okay.
Okay.
Okay. The previous about the error of the in the pi and ground singlet triplet pi is larger, around 3%.
Okay, okay. You're talking about
actually?
the energy difference. Okay, yeah, yes, yeah. Yeah. Yeah, that means because in this case we have used the basic is single reference theory. Coupled cluster simply is the single reference theory. So it may happens that for some excited state, the multi-reference theory is required. So that's why this energy is not that accurate. There is a difference of approximately 4%. Yes.
So this is because
It may be, I'm not sure that that can be the only reason. It may be due to the multi-reference character of that particular excited state.
reference. Okay.
Multi-reference character, yeah.
Oh, multi-reference. Okay.
Yeah.
Yes. Okay. Okay, thank you. Next.
Thank you.
Next, the participant, if you have question, please ask. And maybe me again. So is it this or this about this quantum chemistry? Is it have relation about the physical chemistry? For example, of now we start. I mean this. If, for example, if we explain physical chemistry about Gibbs free energy, and is this any relationship between potential energy and Gibbs free energy actually?
Actually, because I'm not from the chemistry background, so
Yes.
I don't remember actually at this
Okay.
moment that exactly what is the Gibbs free energy. I have some idea that it is related to some ionization energy or so, but at this moment I not exactly remember then what it is.
Okay.
Yeah.
Potential this. Okay, this about potential energy. Yeah. Okay. And then okay. Participant, please ask question. So what is your city actually in India? Is it in the north part, right?
Sorry. What
Sorry.
is
What is your I mean you are stay in the which city now?
which I don't understand what you are asking actually.
Sorry, I just asked another outside of the topic actually. I mean,
Okay. Yeah. Just ask me once again.
yes, your city uh, where are you
Okay.
staying now?
In India, my native place is Punjab.
Punjab.
That is just at the top of if we see the Indian map,
Yes.
this on the top there is Jammu and Kashmir, and below that there are two states, Delhi, Punjab, Haryana. I mean,
Punjab.
from the north part of the India, yeah.
Oh, okay.
From the north part of the India, yeah.
And how was the situation of the now? Is it the COVID?
Yeah, COVID. You're talking about the COVID-19 situation,
Yes.
right? Yeah. COVID-19 situation is much better nowadays, actually, because the vaccination rate is increasing continuously.
So this decrease, right?
Yeah. It is better, much better now. Yeah.
Oh, okay.
Means after the second wave, it is now better. Yeah. Means the
Okay.
second wave, after the second wave, it is better. Means from last 3-4 months, the situation is under control.
Oh, okay.
So everything is open here now.
Yes.
Mostly means all the transportation and everything.
Okay.
Yeah.
Great. Also in Indonesia now it's getting better now after vaccination.
So you have in Indonesia they have lifted up the border restriction, means now the foreigners are allowed. Means the foreigners are allowed now to Indonesia.
Now still work from home, I think.
No, work from home, and foreigners are allowed to come there. Means they have lift up the border restriction.
But still very restricted, I think.
Okay. Yeah.
Still because need to stay quarantine in or staying first in a hotel to check about PCR test and etc.
Okay, fine. Yeah.
Okay. is there any question from participants? Please ask. Do this. Bin, hello Bin, Bin, Bin. Maybe this is another my colleague from Spain. Hello Bin, Bin Yamin. Hello.
Hello, Salma. Hello.
Yes, yes. Can you
Yeah.
hear me? Yes, yes.
Yeah. I'm listening, but I was a bit late. That it's a very early morning here.
Oh yeah, I'm sorry.
Yeah.
It's okay. It's okay. Yes, yes, yes. How are
Yeah,
you?
I was listening to some of the slides. I mean, some 20 minutes or 30 minutes. Last 30 minutes, I was listening.
Okay.
Yeah, I'm fine. I'm fine. Thank
Good.
you. Yeah,
Okay.
you are doing very good. Yeah. Proud of you. That
Do
is
you
a
want to
Erasmus
ask?
mate.
Do you want to ask question, please?
Actually, no. I mean, you covered the questions. I also would be wondering, but yeah, it's fundamentally physics based systematic study, of course, for the diatomic systems. And then the theory behind the excitation energy and so on, actually, the speaker explained very good. I see. And I actually, to be honest, didn't have any pending questions, Yeah, thank you for asking.
Okay. Thank you, Bin.
Yeah,
Thank you
thank
very
you.
much. Yes. Okay. If another question. Okay. No. I think no question.
Oh,
Okay.
thank you.
Okay. I give this session to the MC. So thank you very much. Very interesting lecture and very good presentation. Thank you. I'm very happy and thank you very much.
Yeah,
Okay,
thank you so much for inviting me for this lecture.
Yes, it's very interesting. Okay, next I'll give this to the MC, Mr. Kenny Purwendono.
Okay, thank
Hello.
you. Thank you, Dr. Enubala and Dr. Salma Haminati. Also, thank you for your interesting presentation. Now, I would like to invite Associate Professor Alwar, PhD, as the head of Master of Chemistry Studi Program of Universitas Islam Indonesia, to give the certificate to Dr. Enubala. To Dr. Alwar, please.
Okay, yeah.
Okay, yeah, please.
Okay. Good afternoon, Dr. Renu Wala, PhD. Thank you for your delivering speech today. It's a very nice talk here about the quantum chemistry. And at this moment, I'm going to give what do you call that? A certificate. Yeah, certificate. Thank you very much for your collaboration in our department. Okay, Pak Gani, maybe you can show the certificate. Okay, this is a certificate of appreciation.
Okay, thank you.
Renewable PhD. I hope that it is not the last meeting we are going to do now. We have this is the first time, I think. So we will can arrange for the next time, I think. Thank you very much, Renewable.
Sure. Thank you.
Yeah, thank you to Dr. Alwar and Dr. Renubala. We hope we can invite you offline to our chemistry department in Universitas Islam Indonesia next time after coronavirus pandemic is over. So thank you very much for everyone. Thank you for your participation and attention. See you again in the next event held by the Department of Chemistry, Universitas Islam Indonesia. Good afternoon and wassalamualaikum warahmatullahi wabarakatuh. Thank you. Thank you very much.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you. Thank you. Bye-bye.
Okay. Thank you, Pak Gani.
Thank you. Bye-bye.
Thank you, Bu Reni. Bu Salma. Bu Salma. Okay, thank you. Bye.
Okay. Bye-bye.
Bye-bye.